Welcome to this problem walkthrough. Today, we'll explore the problem number 216, combination sum 3. In this problem, we'll dive into generating combinations that meet specific criteria, and we'll discuss various strategies to solve it. Let's get started. In this problem, we are tasked with finding all valid combinations of k numbers that add up to a given target sum n. The numbers we can use are strictly limited to integers between 1 and 9, and each number can only be used once in a combination. Additionally, the solution set must be free of duplicate combinations, but the order in which the combinations are returned does not matter. The input consists of two integers, k, which represents the number of integers we need to select, and n, the target sum we aim to achieve. The constraints are that k ranges from 1 to 9, and n ranges from 1 to 60. The output will be a list of lists, where each inner list contains a valid combination of k distinct numbers from 1 to 9 that sum up to n. Now let's look at a few examples to better understand the problem. In the first example, we are given k equals 3 and n equals 7. Here, we need to find all possible combinations of three distinct numbers from 1 to 9 that add up to 7. The only valid combination is 1, 2, 4, so the output is 1, 2, 4. Next, for k equals 3 and n equals 9, we need to find combinations of three numbers that sum to 9. In this case, there are three valid combinations, 1, 2, 6, 1, 3, 5, and 2, 3, 4. Thus, the output is 1, 2, 6, 1, 3, 5, 2, 3, 4. These examples demonstrate how to identify combinations that satisfy both the sum requirement and the condition of using distinct numbers. Looking closer at the second example where k equals 3 and n equals 9, we can see the three valid combinations listed explicitly. The first combination is 1, 2, 6, which uses three distinct numbers to reach the target sum of 9. Similarly, 1, 3, 5, and 2, 3, 4 are valid combinations that satisfy the same conditions. Now, consider the third example with k equals 4 and n equals 1. Here, it's impossible to select four distinct numbers from 1 to 9 that sum to 1, so the output is an empty list. This demonstrates that not all inputs will yield valid combinations. Additionally, the problem has constraints: k must be between 1 and 9, and n must fall within the range of 1 to 60. Finally, let's consider some edge cases. For example, when k equals 1 and n equals 10, it's invalid because the largest number we can use is 9, so 10 is out of range. On the other hand, for k equals 9 and n equals 45, the combination is valid because the sum of all numbers from 1 to 9 is exactly 45. However, if we increase n to 46 while keeping k equals 9, the problem becomes invalid because 46 exceeds the sum of all numbers from 1 to 9. Another edge case to note is when k is greater than n, this will always be invalid since we cannot pick more numbers than the target sum allows. These edge cases help clarify the boundaries of the problem and ensure we handle all possible scenarios correctly. When considering how to solve combination sum 3, the brute force approach is the most straightforward way to start. The intuition here is to generate all possible subsets of numbers from 1 to 9. Once we have these subsets, we can check each one to see if it meets the two key conditions. First, does the subset contain exactly k elements? And second, does the sum of these elements equal n? While this approach is conceptually simple, it's extremely inefficient. Generating all subsets of the numbers 1 to 9 involves creating 2 to the power of 9 subsets, and then we need to perform checks on each of them. This results in an exponential time complexity, which makes this method impractical, especially as the input size grows larger. So while it's a good starting point to understand the problem, it's clear we need a more efficient solution. To address the inefficiency of the brute force approach, we can turn to a backtracking strategy. Backtracking is a more systematic way to explore all possible combinations, while pruning unnecessary paths that cannot yield valid results. The core idea is to use a helper function to build combinations recursively. At each step, we attempt to add numbers from 1 to 9, but we impose several important constraints. First, we ensure that we don't reuse numbers in the current combination. Second, we stop adding numbers if the running sum exceeds n. Third, we ensure that the combination doesn't exceed the required size of k elements. If any of these constraints are violated, we backtrack by removing the last number added and trying the next possibility. This approach is much more efficient than brute force because it avoids generating invalid subsets and focuses only on promising paths. By pruning early, we significantly reduce the size of the search space. Now, let's focus on why backtracking is the chosen strategy for this problem. We begin with a few key observations. First, the numbers are restricted to the range of 1 to 9, which is a small and manageable set, making backtracking particularly effective. Second, a valid combination must satisfy two constraints: the size of the combination, k, and the sum of its elements, n. These constraints allow us to terminate invalid paths early, saving computation time. Third, since each number can only be used once, we need to carefully track which numbers are currently included in the combination. The aha moment here is realizing that backtracking allows us to systematically explore all valid combinations while avoiding unnecessary work. This method is ideal because it efficiently prunes paths that don't satisfy the constraints, ensuring we only focus on promising candidates. The recursive nature of backtracking also makes it well suited for handling problems with fixed-size combinations and constraints on numbers. Finally, let's compare the trade-offs between the brute force and backtracking approaches. On one hand, brute force is simple to implement but computationally expensive, with a time complexity of 2 to the power of 9, due to the sheer number of subsets generated. On the other hand, backtracking is slightly more complex to implement, but far more efficient. Its time complexity is approximately 2 to the power of k, in the worst case, where k is the size of the combination. However, in practice, pruning drastically reduces the number of paths explored, making it much faster. Space complexity for backtracking is k, as it requires storing the recursion stack for the current combination. Overall, backtracking is the optimal choice for this problem because it offers the best balance between performance and implementation complexity. By systematically exploring possibilities and discarding invalid paths early, it provides an elegant and efficient way to solve constrained combination problems like this one. To tackle the problem of finding all subsets of numbers from 1 to 9 that contain exactly k elements and have a sum equal to n, we begin by breaking it down systematically. First, the input consists of two integers, k, which specifies the number of elements in each subset, and n, the target sum we aim to achieve. The output is a list of all subsets that meet these criteria, where each number can appear only once, and the numbers range from 1 to 9. To solve this efficiently, we use the backtracking approach. Backtracking is ideal for this problem as it allows us to explore potential combinations while pruning invalid paths early, which is much more efficient than brute force. Finally, we define state variables to manage the backtracking process, ensuring that the algorithm tracks progress and avoids revisiting the same combinations unnecessarily. The key state variables in the backtracking algorithm include the current combination, which keeps track of the numbers we've selected so far, and the current index, which ensures we only consider numbers larger than the last one in the combination, avoiding duplicates. We also track the remaining sum, representing how far we are from reaching the target n, and the remaining elements, which tells us how many more numbers we need to pick to reach k. The backtracking function itself has two base cases. If the remaining sum and remaining elements both reach 0, we add the current combination to our result. On the other hand, if either the remaining sum becomes negative or the remaining elements drop below 0, we terminate that branch early. The recursive step involves iterating through numbers starting from the current index, adding each to the current combination, updating the remaining sum and elements, and then calling the function recursively. After exploring a number, we backtrack by removing it from the combination to try the next possibility. Now, it's important to handle edge cases to ensure the algorithm runs efficiently and correctly. For instance, if k is greater than 9 or n exceeds 45, the maximum possible sum of numbers from 1 to 9, we can immediately return an empty result since valid subsets are impossible. Similarly, if k is 0 or n is less than or equal to 0, we return an empty result. To avoid duplicates, combinations are generated in non-decreasing order by always choosing numbers greater than or equal to the current index. This ensures that 1, 2, 3 is treated as identical to 3, 2, 1 and avoids counting it multiple times. The algorithm also benefits from pruning, where invalid paths are eliminated early based on the remaining sum and elements, reducing unnecessary computations. Additionally, we use efficient data structures. The result list stores all valid subsets, a temporary list tracks the current combination, and the recursive stack implicitly manages the backtracking process. The code implementation of the backtracking algorithm is concise yet powerful. It begins with a helper function, backtrack, which takes the current starting index, remaining sum, remaining elements, and the current combination as parameters. Within this function, we define two base cases. If the remaining sum and elements both reach 0, we add a copy of the current combination to the result list, as it represents a valid subset. If either the remaining sum becomes negative or the remaining elements drop below 0, we terminate that recursive path since it cannot lead to a solution. The recursive case involves iterating through numbers from the current index to 9, adding each number to the current combination, updating the remaining sum and elements, and performing a recursive call. After exploring that branch, we backtrack by removing the number from the current combination, allowing us to test the next number. Finally, the result is returned after all possibilities have been explored. Analyzing the complexity of this algorithm reveals why backtracking is efficient for this problem. The time complexity depends on the number of valid combinations, which is bounded by the mathematical combination formula C(9k). This is because we are selecting k numbers from a set of 9. The space complexity is proportional to the recursion depth, which is O(k), since the maximum depth of our recursive calls corresponds to the number of elements in each combination. Additionally, we must account for the space required to store the result list. Let's walk through an example with k equals 3 and n equals 7. Initially, the current combination is empty, and the remaining sum is 7. Adding 1 gives a new combination, 1, with a remaining sum of 6. Adding 2 results in 1, 2, with a remaining sum of 4, and adding 4 reaches the base case where the remaining sum and elements are both 0. The combination 1, 2, 4 is added to the result. Backtracking then explores other branches, ultimately returning 1, 2, 4 as the solution for this input. This Python solution solves LeetCode problem number 216, combination sum 3, using a backtracking approach. The combination sum 3 method takes two inputs, k and n. The goal is to find all unique combinations of k numbers from 1 to 9 that sum up to n. The core of the solution is the backtrack helper function, which performs the recursive exploration. Explanation of the code. 1. Base case, the function checks if both remaining_k, remaining numbers to select, and remaining_sum, remaining sum to achieve, are 0. If true, it appends a copy of the current combination, path, to the result list. 2. Iterative step, the loop iterates from start, to avoid reusing numbers, through 9. It ensures that the current number I does not exceed the remaining sum, pruning unnecessary paths. 3. Recursive call, if I is valid, it is added to the path, and the function recurses with updated parameters. Remaining_k 1 fewer number to select. Remaining_sum I updates the target sum. I plus 1 ensures the next number is strictly greater. For backtracking, after returning from the recursion, I is removed from path to explore other combinations. 5. Result storage, an empty list result is initialized before calling backtrack. Once all valid combinations are found, result is returned to the caller. Key optimizations. Early exit, if I remaining_sum, the loop breaks. This avoids unnecessary recursive calls. Avoids duplicates, by always starting the next number from I plus 1, combinations are unique. Complexity analysis. Time complexity, the algorithm explores subsets of size k from numbers 1 to 9. In the worst case, this is bounded by 2 to the power of 9, all subsets. Space complexity, the recursion stack depth is at most k, and additional space is used to store combinations in result. This solution is efficient and adheres to the constraints, ensuring correctness for all valid inputs of k and n. This is the Java implementation of LeetCode problem number 216, combination sum 3. The logic mirrors the provided Python solution, utilizing recursion and backtracking to generate all valid combinations. Key differences include the use of Java-specific collections like ArrayList and explicit type declarations for variables and method parameters. The backtrack method recursively builds combinations, and the base case ensures that valid results are captured when both remaining k and remaining sum reach 0. To solve this problem, we need to find all combinations of three numbers that sum up to 7, where each number is between 1 and 9, and no number repeats. We begin by calling the backtrack function with the initial parameters, remaining_k set to 3 because we need three numbers, remaining_sum set to 7 as the target sum, start set to 1 to ensure we only consider numbers from 1 onwards, and an empty path and result. In the first step, we loop through numbers starting from 1. Adding 1 to the path gives us 1, and we make a recursive call to backtrack with updated parameters. Remaining_k decreases to 2 because we now need two more numbers. Remaining_sum decreases to 6 because 7 minus 1 is 6, and start increases to 2 to avoid reusing numbers. Next, in this recursive call, we add 2 to the path, resulting in 1, 2, and call backtrack again with remaining_k now 1, remaining_sum 4, and start 3. Then, we add 3 to the path, making it 1, 2, 3, and call backtrack with remaining_k 0 and remaining_sum 1. However, since remaining_sum is not 0, this path is not valid. We backtrack by removing 3, reverting the path back to 1, 2. After backtracking, we try adding 4 to the path, which changes it to 1, 2, 4. Now, we call backtrack with remaining_k set to 0 and remaining_sum set to 0. This time, both conditions are satisfied, we have exactly three numbers, and their sum is 7. Therefore, we add 1, 2, 4 to the result. After adding this valid combination, we backtrack by removing 4, reverting the path to 1, 2, and continue exploring other possible combinations. Following a similar process, we try other numbers, but none form valid combinations. Thus, for the first example, the final result is 1, 2, 4. Moving to the second example, where k is 3 and n is 9, we start by calling backtrack with an initial remaining_k of 3, remaining_sum of 9, and an empty path. Adding 1 to the path gives 1, and we call backtrack with updated parameters, remaining_k 2, remaining_sum 8, and start 2. Then, adding 2 to the path results in 1, 2, and we call backtrack with remaining_k 1, remaining_sum 6, and start 3. At this point, we explore multiple numbers. Adding 3, 4, and 5 to the path in separate recursive calls allows us to test each potential combination. Only 1, 2, 6 meets the criteria of having three numbers that sum to 9, so we add it to the result. Then, we backtrack to 1 and try adding 3, which leads to recursive attempts with 4, 5, and so on. Through this process, we find another valid combination, 1, 3, 5. Finally, after backtracking again to an empty path, we start with 2 and repeat the process, eventually adding 2, 3, 4 to the result. This gives us a final result of 1, 2, 6, 1, 3, 5, 2, 3, 4 for the second example. Now, for the third example, where k is 4 and n is 15, we extend the process to handle four numbers. Starting with 1, we recursively add numbers such as 2, 3, and so on, always backtracking when needed. Through this approach, we find valid combinations like 1, 2, 4, 8, 1, 3, 5, 6, and 2, 3, 4, 6. These combinations form the final result for this example, 1, 2, 4, 8, 1, 3, 5, 6, 2, 3, 4, 6. To analyze the time complexity of this solution, we start with the recursive backtracking approach. The recursion explores combinations of numbers from 1 to 9. At each step, the algorithm decides whether to include or exclude a number. This process continues until one of two conditions is met, either the combination reaches the desired size, k, or the remaining sum becomes negative, at which point the branch terminates. The maximum depth of this recursion is k since every valid combination must have exactly k numbers. Additionally, at each level, the algorithm iterates from the current starting number to 9, reducing the pool of choices at deeper levels. The total number of recursive calls is determined by the number of combinations of k numbers from the set 1, 2, 9, which is represented mathematically as C, 9, k, or the binomial coefficient. This gives us the total number of ways to select k numbers out of 9. The binomial coefficient C, 9, k, is calculated using the formula 9 / k * 9k. This represents the number of unique ways to select k numbers from a pool of 9. Now, for each combination, the algorithm performs constant time operations such as adding or removing elements from the current list and checking conditions. These operations do not depend on the size of the combination or the input, which means the work per combination is 1. When we combine the total number of combinations, see 9k, with the constant time operations performed for each, the overall time complexity of the algorithm becomes proportional to the number of combinations. Thus, the time complexity is 9k, or equivalently, 9/k. Asterisk, 9k. Now turning to space complexity, we need to account for both the recursion stack and the space used to store results. First, the recursion stack has a maximum depth of k, as the recursion progresses until the combination reaches k elements. Each recursive call adds a small amount of space for parameters and local variables, making the recursion stack space k. Next, the algorithm stores all valid combinations in a result list. The maximum number of combinations is 9k, and since each combination contains exactly k numbers, the total space used for storing results is k*c, 9k. Additionally, the path list, which holds the current combination during recursion, has a maximum size of k, and this list is reused across calls. The space for path is therefore k. Combining these, the total space complexity is k for the recursion stack plus k*c, 9k for result storage, which simplifies to k*c, 9k. When comparing backtracking to a brute force approach, the advantages of backtracking become clear. A brute force method would generate all possible subsets of the numbers 1, 2, 9, which amounts to 2 to the power of 9 subsets, and then filter out those that meet the size and some constraints. This process has an exponential time complexity of 2 to the power of 9 *k, where k is the size of the combination. Backtracking, on the other hand, avoids generating unnecessary subsets by pruning invalid branches early, reducing the recursive calls to only 9k, which is significantly more efficient for small k. In the best case, where constraints lead to early termination of recursion, fewer calls are made, and the time complexity decreases further. The worst case occurs when all combinations of size k are valid, requiring exploration of all 9k possibilities. To summarize, backtracking achieves a time complexity of 9k and a space complexity of k*c, 9k, making it an optimized solution compared to brute force by focusing only on valid combinations and avoiding redundant computation. When solving this problem, there are a few common mistakes to watch out for. First, failing to prune inefficiently is a major issue. If you don't stop the recursion early when the sum exceeds the target, it leads to unnecessary computation and significantly increases the time complexity, especially for larger inputs. To fix this, always include a condition to return early if the current sum goes beyond the target value. Another mistake is having an incorrect base case in recursion. It's essential to check both conditions in the base case, whether the subset size equals k and whether the sum equals n. If you miss either of these, you risk including invalid solutions or skipping valid ones. Lastly, reusing numbers in a combination is another common error. Since each number from 1 to 9 should be used at most once, you need to ensure that you use a start index to prevent numbers from being reused inappropriately. Now, let's look at a couple more pitfalls. Not handling edge cases can lead to incorrect outputs or even runtime errors. For example, if k is greater than 9, or if n is too small or too large, there are no valid combinations possible. To address this, you should add checks for impossible inputs and return an empty list in such cases. Another common confusion is between permutations and combinations. Generating permutations, which involve different orders of the same elements, is not what this problem requires. Instead, you should focus on combinations, where the order of elements doesn't matter. To fix this, use backtracking with a fixed order, ensuring you're only generating combinations. This problem also comes with some important insights that are worth emphasizing, especially in an interview setting. It's a classic example of combining subset generation with backtracking. The key here is to recognize patterns, particularly when to prune and how to avoid redundant computations. Since the input size is fixed, limited to numbers 1 through 9, the problem is computationally manageable with an efficient backtracking approach. To further optimize, start with smaller numbers to generate combinations in lexicographical order, and use pruning aggressively to minimize the exploration space. Additionally, you should consider how the algorithm behaves under constraints. For example, if k exceeds 9, you can return early since only 9 numbers are available. Similarly, if the sum of the smallest k numbers exceeds n, it's impossible to form a valid combination, so you can exit early as well. There are also related problems that you might encounter, which build on similar concepts. For instance, problem 39, combination sum, is closely related, but it allows repeated usage of numbers, making it slightly different from this one. Problem 40, combination sum 2, is another variation, which prohibits duplicate combinations but still bears similarities. Problems 78 and 90, which focus on subsets, also share elements of this problem. Problem 78 generates all subsets of a given array, while problem 90 extends this by handling duplicates, ensuring no repeated subsets are included in the output. Familiarizing yourself with these problems can deepen your understanding of backtracking and subset generation techniques. Finally, there are alternative approaches to solving this problem that you might consider. One option is using an iterative solution with bit masking. This method generates all subsets and then filters them based on the conditions that the subset size equals k and the sum equals n. However, while bit masking is simpler to implement, it tends to be less efficient than backtracking because it requires generating all subsets. Another approach involves dynamic programming. Here, you can use a DP table where each entry represents combinations of a specific size that sum to a target value. While this method can work, it's more memory intensive and less intuitive for smaller, fixed input sizes like this problem. Lastly, for very small inputs, you might consider a mathematical approach, manually calculating combinations using combinatorics. While this can be quick for small cases, it's not scalable or practical for most inputs. That concludes our walkthrough of the combination sum 3 problem. We covered the key aspects of the problem, discussed approaches, and highlighted important takeaways. Thanks for joining, and don't forget to like and subscribe for more content. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!